In this video, we are going to follow the element hydrogen, the lightest element on the periodic table. Hydrogen's creation started from the formation of the universe. During this event, all the matter and energy that would ever exist was created from a single point. Immediately after its formation, it began to cool. The radiant energy from the Big Bang created a quark gluon plasma, which then became the first protons, neutrons, and electrons. From there, these subatomic particles became the first two lightest elements, hydrogen and helium. Hydrogen 1 is the most common hydrogen isotope, with an abundance of more than 99.98%. The three stable isotopes of hydrogen are hydrogen 1, hydrogen 2, and hydrogen 3. The number of nucleons in the nucleus is the atom's mass number, and each isotope of a given element has a different mass number. There are some flaws in the atomic theory. For example, John Dalton claimed that all matter is composed of tiny, indivisible atoms. We now know that atoms are divisible and composed of smaller subatomic particles. He also stated that atoms of an element are identical in mass. This is incorrect, because all elements have isotopes, which means that atoms of an element do not have to have the same mass. There are some limits to our understanding, but quantum mechanics may be able to solve this limitation. Quantum mechanics deals with laws of physics for extremely small particles at the subatomic level. Many of the behaviors of particles cannot be witnessed and are only described by abstract mathematical models. The quest for a unified theory using quantum mechanics is still ongoing. As technology advances, scientists can run experiments to test theories of how subatomic particles work. Nuclear fusion involves two atomic nuclei joining to make a large nucleus and releasing energy when this happens. The Sun and other stars use nuclear fusion to release energy. The sequence of nuclear fusion is complex, but in general, hydrogen nuclei join to form helium nuclei. Here, hydrogen 1 and hydrogen 2 nuclei collide and fuse together. Unlike other elements, hydrogen was not created in the death of a star or in a lab. Hydrogen was created along with helium in the Big Bang. Hydrogen and helium went to create the first stars. During most of a star's lifetime, hydrogen nuclei are its main fuel source. As the star runs out of hydrogen, other fusion reactions take place, forming the nuclei of other elements. Only 90 of the 116 known elements occur naturally, and the other 26 are found in the development of nuclear power plants and machines known as particle accelerators. Scientists discovered that by allowing fast-moving neutrons to collide with the common isotope of uranium in a nuclear reactor, the new element plutonium was made. The other way is by smashing atoms together in machines known as particle accelerators. It was also discovered that new elements could be made. Elements that don't currently exist can be created but are highly unstable. Scientists can synthesize elements with the higher atomic numbers. But it's not really the element itself that is seen, but a decay product that can be witnessed for a very short time. The emission spectrum of a chemical element or chemical compounds is the spectrum of frequencies of light that an atom can emit are dependent on the states of the electrons can be in. When excited, an electron moves to a higher energy level or orbit. When the electron falls back to its ground level, the light is emitted. There are many possible electrons transitions for each atom, and each transition has a specific energy difference. This collection of different transitions, leading to the different radiated wavelengths, makes up the emission spectrum. Each element's emission spectrum is unique. The left side of the spectrum contains the colors of the highest energy levels, like violet, and the right side of the spectrum contains the lowest energy levels, like the color red. When hydrogen jumps down an energy level, it gives off a light that resembles a pale blue flame that is almost invisible to the naked eye. Because of the pale blue cover it gives off, we know that hydrogen has a fairly high energy level. There are many new technologies that are being developed that help scientists monitor chemical changes in our environment. Light-based technologies like the spectroscopy are going through advances that make readings more accurate and use better computers to post-process the information. Improvements to image technology like the PET and MRI allow scientists to witness chemical changes at improved levels. There are multiple patterns and trends in the periodic table of elements. Pattern 1 is the atomic number pattern. Elements on the periodic table are ordered by their atomic number, which is also the number of protons. Pattern number 2 is a row on the periodic table is called a period. The number of periods indicate how many electron orbitals there are in each atom. The third pattern is that there are groups in the periodic table where the outermost orbital has the same number of electrons in each element. Because electrons are the outermost particles in the atom, they are the ones to give the atom its properties. So elements with similar outer orbitals have similar properties. An example of a group are the alkali metals, which all react violently with water. Pattern number 4 is from left to right across a period of elements, electronegativity increases. And from top to bottom down a group, electronegativity decreases. Pattern number 5 is that the ionization energy of the elements within a period generally increases from left to right. The ionization energy of the elements within a group generally decreases from top to bottom. Pattern number 6 is that electron affinity increases from left to right within a period. This is caused by the decrease in atomic radius. Also, electron affinity decreases from top to bottom within a group. This is caused by the increase in atomic radius. Pattern number 7 is metallic characteristics decrease from left to right across a period. In addition, metallic characteristics increase down a group. Hydrogen has an atomic number of 1. It is the first element in the periodic table, and it has 1 proton. Hydrogen is in the first period, and it has 1 electron orbital. Hydrogen is in group 1, and it has 1 electron in its outer orbital. Hydrogen fits in with the nonmetals. The first 2 elements, hydrogen and helium, have caused disagreement as to exactly which groups they should be assigned to. In the modern periodic table of elements, they fall into groups 1 and 18 respectively. The result is a rather awkward twin tower shape to add to the already uneven shape the periodic table has. Hydrogen can lose as well as gain an electron. As a result, it can be placed into group 1 as it usually is, or with the halogens in group 17. It has even been suggested that hydrogen should be grouped at the head of the carbon group since, like carbon, it's an atom that has a half-filled outer shell. Some scientists believe that the table can be improved by arranging it in a circular form. This gives a sense of relative size of the atoms. The closer to the center, the smaller they are. This is something that is missing from the current form of the table. It preserves the periods and groups that make the current table so useful. And by placing hydrogen and helium near the center, it solves the problem of whether to put hydrogen with the halogens or the alkali metals, and whether to put helium in the second group or with the inert gases. Electronegativity is a measure of the attraction of an atom for electrons in a chemical bond. The higher the electronegativity of the atom, the greater its attraction for bonding electrons. Hydrogen readily forms covalent compounds with most nonmetallic elements. In ionic compounds, hydrogen can take form of the negative charge known as a hydrid. Hydrogen forms many compounds, many of which are water, or H2O. Hydrogen is a colorless gas that is lighter than air. Mixtures of hydrogen gas and air do not react unless ignited with a flame or spark, in which case the result is a fire explosion with a characteristic reddish flame whose only product is water. Hydrogen is no more or less dangerous than other flammable fuels, including gasoline and natural gas. In fact, some of hydrogen's differences actually provide safety benefits compared to gasoline or other fuels.